Here is another optimization problem that's going to be a little bit more involved than the last one. This problem says Chris wants to make pins for his 9 reindeer. He constructs the pins alongside the workshop as shown, and I'll show you the picture of that in a minute, with 9 equal sized pins created with 10 portions perpendicular to the building and 1 long portion running parallel to the workshop. If he has 4,500 feet of fencing available, what dimension should each pin have to maximize each reindeer's game playing area? And the parenthetical for this says Chris does not place fencing along the shared side with the workshop. So let's read through this one more time and pick out the information that we need. We know that there's 9 reindeer. Each reindeer is going to get its own pin. So that means that we want to have 9 pins of equal size. It also talks about having 10 portions perpendicular to the building and 1 long portion running parallel to the workshop. Next, it says that he has 4,500 feet of fencing available to build all of these pins. So the amount of fencing he has to use for all the pins total is 4,500 feet. Here's Chris's workshop here, this big rectangle. All the new stuff is off here to the side. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 new pins that are being built. We're trying to maximize the pin size. Notice the shape of these. These are rectangular. So we're trying to maximize the area of a rectangle. That clues us in to what our objective function is going to be. The area of a rectangle is length times width. That's our objective function. And that is all the information that we have. So let's look at this diagram again. We're trying to maximize the area of all these pins. So let's just focus on a single pin. Since we're using the wall of the workshop as one of the sides, that means that we're just fencing in 3 sides of the pin. And we're trying to find the area of that pin. Now it's time to define some variables. First, let's call the length x. So we're using x amount of fence for 2 sides of the pin. The other side is the width, and we're going to call that y. So we're only using y lengths of fence for 1 pin. The opposite side of the y is the wall of the workshop, where we do not have to fence. The area of 1 pin is just length times width, and this is what we're trying to maximize. And in terms of our variables, x and y, length times width is just x times y. Since we have 9 pins total, and they're all the same size, then the area of all 9 pins is going to be 9xy. And that, once again, is our objective function. So now let's think about how all of these pins are going to be fenced. We already know that we're using the workshop as one side of the pins, so we don't have to worry about fencing anywhere where the workshop already exists. So let's get rid of the workshop. The right side of the pin, that could be one continuous piece of fence. Each of these smaller segments of fence, these are our lengths, x. Each of those is equal to x. And then this longer piece of fence represents all of our widths added together. 1 pin had a width of 9, and since we have 9 pins, that means that our width is in total equal to 9y. So the total amount of fence that we're using here is all of the lengths added together, so that would be 10x plus the width, which was 9y, and that has to equal the total amount of fence that we have available, which is 4,500 feet. This is our constraint function. So let's think about what we know so far. We know that our objective function is the area of all of our rectangles put together. This is a multivariate function. The area is equal to 9 times x times y. And we know that our constraint function is 10x plus 9y equals 4,500. Since we need to take the derivative of our area function, we need to redefine it in terms of just a single variable. So in order to do that, we can use our constraint function and solve that for a variable. I'm going to solve this for y. So move the 10x over to the other side of the equal sign and then divide both sides by 9. Take this and substitute it back into your area formula. That means that our constraint function is now just a function of a single variable, x, and that's equal to 9x times 4,500 minus 10x over 9. Before taking the derivative, it would be useful to simplify this a little bit. That 9 out front will cancel with the 9 in the denominator, and after distributing the x, this would simplify to 4,500x minus 10x squared. Since our objective function is a polynomial, I'm just going to use the second derivative test. A prime of x would be 4,500 minus 20x. Under the second derivative test, we need to set a prime equal to 0. We also need to see if A prime fails anywhere, and if so, where does it fail? If we set A prime equal to 0, that means that we'd have 4500 minus 20x equals to 0. And now we can solve for x. 4500 divided by 20 is 225. So x equals 225 is a critical value. Now, does A prime fail? Since A prime was a polynomial, that means the derivative of that will not fail. Now we can find the second derivative. The second derivative would be equal to negative 20. We have to plug in our critical value of 225. Notice that there is no x for us to plug it in, so it doesn't matter what we plug into this, we're always going to get negative 20. That means that A double prime of 225 is negative. Since the second derivative is negative, that means we have a convex function, or in other words, is concave down. So therefore, by the second derivative test, the area has a relative max at x is equal to 225. Alright, so x is equal to 225. Let's scroll back up and look at what the problem was asking us. The question was, if he has 4,500 feet of fencing available, what dimension should each pin have to maximize the area? What dimension, or what dimensions would probably be a better wording for this. That's what we're specifically trying to answer. So x equals 225, that's not going to be good enough. The way we set up this problem, x was the length of a pin. We need to find the dimensions of a pin, which means that we also have to report the width. That is going to be the y value. We have an equation for y as a function of x. That is, y is equal to 4,500 minus 10x divided by 9. We know that x is equal to 225 is one of our dimensions, so just plug that in to this y equation. So then to answer the problem, the area is maximized whenever the length is equal to 225 feet and the width is equal to 250 feet.